Good.
Oh, okay. So it's my pleasure to introduce Professor Larsson from Linköping University in Sweden. He'll talk today about quantum computation and the additional degrees of freedom in quantum bits. So, please.
Yes, so I promised to talk about quantum computing and physical degrees of freedom. I also promised to talk about contextuality and the quantum speed up, and I might not have enough time for that. Let's see what happens. So the picture on screen is actually a classical machine that runs a quantum algorithm. And the reason that this would work is that we have managed to understand what makes the quantum algorithm actually work. And I will try to explain how that is possible. I could reveal immediately that the picture that you're seeing is a classical machine using the quantum algorithm to factor the number 15. It's Shor's algorithm. But Shor's algorithm in this kind of machine still has large systematic errors, and I will try to explain the reasons for that too. But let's get the show on the road. Okay, so quantum computers can solve certain types of problems much faster than a standard machine can do. And these problems are typically of the kind you want to find an overall property of a function, and you need exponentially many function calls to do that. A quantum computer might not need so many calls. It might be satisfied with just one function call. And the setup is on the screen that you typically have the function call in the middle, and then you have some extra gates from the quantum regime, in this case, Hadamard gates. And at the end, you measure. In the beginning, in the start here, I hope you can see the cursor. I was going to point with something else, but I hope you can see the cursor. You can send in data here, and the question is a little: what is going on here? Why are we getting the quantum speed up? How is the function? How is the? Let me check the chat here. There are two messages. I hope there's nothing serious. Okay. How is the quantum machine able to do this? So a standard machine uses logical bits and logical gates. You're used to that. You build it up from NOT gates, XOR gates, AND gates, or OR gates indeed. And what you're after here is to have addition and multiplication, the XOR gate and the AND gate, so to speak. And you build up more complicated functions by combining these in several steps. In a classical reversible machine, the gates look different, but they're still classical gates. You've got the XOR gate that provides the notation for the quantum C0, the controlled NOT. That's in classical reversible computing, that's an XOR gate. And the multiplication you get from the Toffoli gate, which has the same symbol in classical reversible computing as it has in quantum computing. And again, more complicated functions are built here in several steps. You typically build up some complicated function, and you want to find some overall property of the function. You can build all the functions because you have both addition and multiplication, and this particular function that is on the view graph here, that has the property of being balanced. So if you look at the table of values here, 4 of the values give the 4 of the inputs, possible inputs of 3 bits, give the output 1, and 4 of them give the output 0. So it's balanced. You might also have constant functions, which would only have the number 1 or the number 0 in the right hand column. And checking if a function is balanced or constant, it might need testing the first half here. So if you get all ones for the first 4 values, you still don't know if the function is constant or balanced. So you need exponentially many inputs. You increase the number of values you need to test with that increases as 2 to the n, so exponential. While a quantum machine can manage much better. You use particular gates before and after to prepare some quantum state that you send into the quantum representation of the function. And then on the output, you can check here in the measurement if it's a constant or a balanced function. A constant function would give the value 0 in this particular case, and a balanced function would give the value, well, different from 0. So if you get something that is different from 0, you know that it's a balanced function in one function call. You don't need the full table, and you certainly don't need exponentially many function calls. How is this possible? Well, a quantum computer extends the gates to quantum gates, but not only the standard gates from reversible computing, you also got new gates that create superpositions. Here I give the example of the Hadamard gate, but in general you could think of Fourier transforms. This is actually a Fourier transform also. It's the Fourier transform mod 2. So the exponential function you typically see in a Fourier transform isn't visible here, but it's really e to the I pi over 2. E to the I pi, I mean. Okay, so let's view this from a different point of view. So let's look at the controlled knot, which you know how it works. It adds the top bit to the bottom bit. And you also know that it preserves superposition. So if you've got the plus state, which is the first one output from the Hadamard here, you input a 0, the plus state is a superposition with a positive phase. And if you've got this on the input, you've got the tensor product of this, but you could also represent it as you either have the 0 on the input or the 1 on the input. In both cases, you have the 0 on the output. And the C naught adds this, well, it copies the value of the first bit to the second bit. So now you've got an entangled state on the output. You can create entangled states by using this. So if you now have a function that operates on your input, you could in principle calculate the function output for every value of the input. And now the next question is, can we now check if the function value are equal or if they are different? In this simple case, equal function values would mean the function is constant, and different function values would mean the function is balanced. The standard explanation is that you do this on the full register. So n qubits input, you do the Hadamard on all of them, and you create a large superposition here. You input that to the function, and you calculate everything in parallel. For all possible input values, you calculate the output. The expression is like this, a sum of all cats over all the inputs. So the argument is the calculation is done in parallel for all of them, and that the parallel results are combined by interference in this Hadamard here. And the measurement outcome after having done this interference will give you the correct answer. I'm going to try to argue to you that this is not the best explanation. There's a different explanation that will give you a better understanding of what is going on here. Let's look again at our example. So I'm going to use this as a simple function, the simplest possible function that you could think of, addition modulo 2. So it's a balanced function, really. So if you've now got a more complicated superposition, which you have if your input has a Hadamard on both the control and the target qubits, if you now input plus plus, you can easily see that the C0 doesn't do so much to the state. The output is still plus plus. So the tensor product of 0 plus 1 and 0 plus 1. A different example is to have plus and minus. So the tensor product of 0 and 1 with a positive phase, the superposition, and 0 and 1 with a negative phase in the superposition. If you now perform the C0 on this state here, what happens is that the third component will change and the fourth component will change. In effect, what you do is you reorder the pluses and minuses here. And on the output, you find this tensor product, which means that the system has changed state, minus, minus. If you do that for all four, you get this table. The examples we had is this one and that one. If you do the same kind of calculation for the other four, you get these expressions. And you know, and I know, that superposition can be created in this gate here. 0 creates the plus state, 1 creates the minus state. So adding these gates, you get a different map. If we add them to all four, we get this kind of map. And you can see that it creates a familiar pattern. Somehow zeros pass through, 0 and 1 here. So something copies this 1 here to the top. The same happens here. Well, nothing happens here because the 0 does not influence the top value. But if we got a 1 on the target, the control changes. So what we've just proven is a well-known result from basic quantum computing called the phase kickback identity. The C0 is addition modulo 2 in the computational basis, but also addition modulo 2 in the backward direction, but in the phase basis. And if our black box here is a C0, which means it's a balanced function, the influence from the C0 here will be turned upside down. For a constant function, on the other hand, the box would be empty, or perhaps contain an inverter here, a simple constant inverter, which means that the Hadamards simply cancel. Nothing will happen to the inputs. And of course, that's really crucial for our quantum algorithm. What you do is you insert something that you know what the input values are, and then you check on the output. Has the output changed? Then there's a C0 in the box. Has the output not changed? There's no connection between the two. So we have a different explanation now. I mean, the important thing here is that the map that you have in the forward direction does something else in the backward direction inside the Hadamard. So the standard explanation might be better talked about as shifting information that is in the computational basis to something that contains information in a different basis, the phase basis. The Hadamard transform is really the bitwise discrete Fourier transform mod 2. And you probably know that the Fourier transform does not change anything. It's a basis change in the vector space we're using for our description, which means it changes, it writes information that was in the computational degree of freedom to the phase degree of freedom. You could think of it as a change from time to frequency, or as a change from position to momentum. All of these are connected by Fourier transforms. What you really do is write information in the conjugate, the canonically conjugate degree of freedom to the one that you're used to looking at. So the central point here is that the function contains a calculation made also in this new degree of freedom, the phase degree of freedom. The Hadamard on the inputs write the information that you put on the input, it writes it into the phase degree of freedom. And then, well, the quantum algorithm here performs some calculation in F. But on the outputs, we have Hadamard that retrieve the information from the same degree of freedom. So there's calculation going on here in the function box, but it's in the phase degree of freedom, and it takes inputs from the bottom and output. It's makes the output on the top. So it's two calculations, two different calculations. Either, if you're interested in the function value, you do the calculation in the forward direction. If you're interested in this overall property that you're looking for, in Deutsch-Rosa, it's whether the function is constant or balanced, then you do a different calculation in the backward direction, and the access to this different calculation is given to you by the Hadamard or the Fourier transform. And I believe this is a better way to understand what is going on here. It really is two different calculations, but in this world, in two different degrees of freedom. It's not what the standard explanation where you've got superpositions of many different inputs and you do all the calculations for all the values in parallel. That's not what you do. You don't do calculations of different function values, different inputs in multiple universes or multiple worlds, in many worlds. What you do is either the function calculation or the overall property calculation. So at this point, you could ask a couple of questions here. What data is used? You could also ask what is actually calculated. You can ask the question, does all quantum algorithms follow this pattern? What I've showed you here is a really, really simple example. And you can also ask the question, what are the requirements on the system? That will tell you something about how difficult it is to build a quantum computer. And I can give you the answers up front because I don't have time to go through all the details. What it turns out that the lower system here is the input and the upper system is the target. So the roles of the registers are reversed. I should point out that one important feature of this is that even though the target is 1 bit, so that the function can only provide 1 bit of information for each call, the control register is n bits, which means that there's much less restriction on how much information a quantum algorithm can give you. And that has profound implications. It means that a single call to this kind of function can give you much more information than a single call to the classical function can. And that's the main reason that the speed up is at all possible. You have a larger register, so you could convey more information out of the function box. What is calculated? Well, in this case, it's clear. It's whether the function is constant or balanced. Structural information about f. Do all quantum algorithms follow this pattern? The answer is yes. There's a theorem by my PhD student that says phase kickback, the same identity that we saw, enables the quantum algorithm for a BQP complete problem, which means, well, BQP is bounded error quantum polynomial time, meaning whatever you can solve in a quantum machine in polynomial time efficiently, that can be solved by using this procedure. So it uses the same thing. And what are the requirements? Well, phase preservation is a requirement here. The map in Deutsch-Osa looks like this. I won't dwell on that. I will just tell you, you can explicitly calculate the map. And you can ask me later or read in our paper about the details. I should probably stress that I don't believe superposition or quantum parallelism is a good explanation. And here's the detailed explanation of why. So imagine you have a unitary which implements f of x. This unitary, what you typically require is that the x value is mapped onto the correct function value here. And that's typically all that's said. It's supposed to be unitary and contain the correct function map. And I will now tell you that this is not enough. You need more. So what I've done here is I've taken this correct unitary and I put it inside the larger box and I put a phase inverter before and after the unitary. And if you do the calculations, what you find is that the function value is still correct, but you have an extra phase before the function value. Now, a textbook in quantum mechanics will tell you that, well, a global phase doesn't matter. Here I will tell you that this actually matters. So the upshot is that the dashed box here still gives you the correct function values. So in a sense, it's a unitary that gives you the correct function values. And if this was enough, you would get the same behavior in the quantum algorithm when you use this one or when you use the lower one. However, the quantum algorithm gives you radically different outcomes. The reason is that when you put Hadamard on your inputs of choice here, you will get the expected linear combination on the output here, but in the lower, but the dashed function box, you would not. The phase is already present for each x, so it will be cancelled here. And when you later on do the measurement, this lower box will tell you that whatever you input, whatever function you have, the function is constant because there's always a 0 on the output here. The lower box will fail consistently, even though it gave the correct function output. And in the picture that I painted for you, the phase inverter here erases the information that you wrote. So there's nothing that can influence the top register. So you get a good explanation of why this does not work also in the picture that I showed you. So it's necessary. We're talking about resources now. So, I mean, you typically see suggestions like superposition and interference are necessary. Or you see, well, entanglement is necessary, or non-locality is necessary, or contextuality is not necessary. You hear things like coherence, or perhaps the continuity of the state space and so on. Well, I'll tell you that what you actually need to have is the ability to read and write in the additional degree of freedom. In this case, the phase degree of freedom. And you also need phase preservation. You can't have the phase eraser in your unitary. You actually need phase preservation, because that will mean that you preserve the information that you put into the additional degree of freedom and that you later read off from the additional degree of freedom. I should point out that I've drawn one case here, and it's not like there's only one case. What happens is that even with a discrete set of gates that you could influence the phase with here, for each correct unitary, you have exponentially many wrong unitaries. So it really is a big problem. You get systematic errors. You can view Shor's algorithm as one example of this also. It's in BQP. Now, I suspect I have too little time to talk about this. Shor's algorithm, you implement this function, multiplication with a to the power x mod n. You're looking for the period of that function. And when you set the thing up, you get periodic behavior. So after the Fourier transform here, you get certain frequencies that give you high probability for certain values for the outputs. Those probabilities give you high probability for getting a output. K here is the measurement output, close to a random quotient with R in the denominator, where R is the period which you're looking for. The example is R equals 6. So you get resonance for multiples of a certain frequency here, and that can also be understood as phase kickback. And I can't really go into the details here, but the number S here is actually a random number that you could think of as being present in the phase of the input, the target input. What we do in my group is trying to extend this more. We have produced a simple model which extends classical reversible logic with an extra degree of freedom. And it turns out that we can reproduce some of the speedup of quantum algorithms in the oracle paradigm. So we think of the function as a black box, which you frequently do in quantum algorithms. And then you can get the exact same speedup. We don't get this in Shor's algorithm because Shor's algorithm is an explicit, you have an explicit construction in polynomial time of the gate array. And using that gate array, we don't get the speedup. But this intrigues us a little, so we try to extend the model to understand better what enables the speedup for real. I think that what we've found here is that this is an enabling feature, but it's not responsible for the speedup as such in a quantum machine. So we are looking for another property of the system that would help us pinpoint what is the actual resource behind quantum computer speedup. And there's very little time left. What the latest thing we did was to try to add quantum contextuality to this model. We studied a problem called the shallow circuits problem, which has a provable gap between the quantum and the classical algorithms. in a particular case, when you use gates with bounded fan-in, then you can prove there is a difference between classical and quantum machinery. And then we extended our simulation framework to reproduce more of the quantum mechanical behavior. In particular, the contextual behavior of the Pauli group. So the quantum contextuality present in the Pauli group. And we managed to do that. We now have a model that tells us how does the contextuality of the Pauli group actually behave? What is the underlying mechanism? And we published this in Official Letters a few years back. I don't have time to go into the details here, but you can look there. And that particular model, it's not quite classical because it re-implements certain features of the quantum mechanical model. And those features that we managed to capture are enough to solve the shallow circuits problem with the same complexity as the quantum machine. The model that we produced is also quadratic in complexity, meaning that it's you can perform it in polynomial time. So our conclusions: the quantum algorithms that we know and love use a second degree of freedom for the crucial component, the enabling thing of the calculation. It is enabled by phase kickback, but it does require phase preservation, and that puts a lot of restrictions on the unitaries that you use in your quantum computer. And we believe that obtaining this is what makes building a quantum computer difficult. It's not enough to have a unitary that gives you the right function map. You also need the right phase map. And we're trying to extend the result by starting from a classical system and adding properties. We're attempting to find the resource behind the quantum speedup, and here's references for the papers. Thank you very much.
So thank you very much. Thank you for sharing us such an intriguing results. Very interesting. So we have some questions, I believe, nowadays in here. So when not, maybe I will use possibility as a chairman to ask question you, Professor Larsson. So just your connection between classical and quantum algorithm and resources for this. There is such activity which is called classical entanglement.
Yes.
Which, and for my understanding, for example, as I understand this situation, so this, of course, not fundamentally classical things, quantum things, of course, but the difference is that we have some degrees of freedom. They are looking like, everything looks like entangled, but only for classical systems. People also argue that this is a resource for quantum computation, but in my understanding, the lack in this case is absence in classical case, rule for this. Is it okay? Is it possible to say that between classical and quantum systems, so we have such things in classical theory and in quantum theory like entanglement or which looking like entanglement, but Born rule distinguish between them. And is it possible to connect with your results so that you somehow say that classical, you may maybe, so far as I understand, you can emulate maybe some quantum algorithm or some resources. And is it possible to say that Born rule is very important here? Story is
no,
a part.
So the answer, my straight answer is no. I think the Born rule is important, but it's important as a let me see. So the Born rule is not what prohibits you from doing this. I'm not sure how to connect it to what I was just saying. So I should point out that both of the models here, the simpler one, with just a simple extension to classical reversible logic that obeys the Born rule. And also the more complicated one here, which reproduces stabilized quantum mechanical behavior. Okay, so that really does obey Born's rule. The previous one, there are systematic errors, this I should say, but this one actually reproduces all the behavior of stabilized quantum mechanics. So it's not as simple as just blaming the Born rule.
Okay, thank you very much. Thank you very much. More questions? I don't see.
I have a question.
Yeah, please.
Jan-Åke, can you say something about, I mean, you mentioned in the summary that the reason for why it's difficult to build a quantum computer, and you gave some arguments, but is it possible to identify different platforms where you think that there could be more progress than with other platforms like trapped ions or trapped neutral particles or atoms or superconducting qubits and so on and so forth?
Yeah, so one problem here is that when you speak to people who build these things, when they explain to you what they are doing, they always say, "Now, so we are trying our best to reproduce a unitary that gives the correct function map." And when I point out to them that no, you need also to preserve the phase,
Yeah.
This is clear to them when you point it out. Yes, of course, we need to do that, but they're not always so clear on that before you had this conversation. So one problem here is that the language they use is not adapted to the actual problem. So I think that this can be used as a tool, yes, but I don't have a good answer for which technology is the better.
Okay.
Yeah. Yeah.
Okay, more questions or comments? I think this is not the case, so let's thank our speaker again. Thank you very much. And now we switch from quantum software